and welcome Mindsetters. You have just joined us on Learn Extra Live, and today we are doing physical science for you grade 12s. I'm Katleha and this is Tebogo. How are you, Tebogo?
I'm well, thanks.
Great. She is one of our top 10 presenters. Please tell us a little bit about yourself, how you got here, anything.
Well, I am studying my BCom internal auditing degree at Tux
Awesome.
University.
Okay.
And I am independent and external motivation, enthusiastic and full of determination, a proud mindsetter too.
Awesome. So you've been a mindsetter for how long now?
For a year. That's when I
Awesome.
discovered it last year in 2012, thankfully in my matric year.
Awesome, guys. You can hear Matrix. I'm so glad that you joined us today because mindset really does help, guys. You've heard the testimonies, you've heard what people have to say, and you even have stuff to say yourself. So let us know. Jump on the page. Our page is www.facebook.com/learnextra. Tebogo will be on the page with you today. So make sure that you ask her. You can hear that she's smart, guys. You can hear that she's been here. She's done that. So you can actually ask her questions and she will be trying to help you the whole day. And of course, guys, random acts of kindness. By now, I hope you have posted your random acts of kindness because we will be doing a lucky draw. If you win today, as you can see, here's the box with all the names. If you win, if you can look behind me here, there is a Cheetos hamper with chips inside it. There's a Cheetos notepad. There's this. It's like a party pack, guys. There's also 5 CDs from Universal. There's Donald. There's Unati. There's Kaya. There's Malik. There's some love songs because it is the month of love. And also from Mindset, there's this t-shirt, an awesome pen, and lanyard. Guys, you win all of this. I can't explain to you how amazing. Aren't these prizes amazing?
Awesome.
Awesome. So, and because you're here today, you have the opportunity to draw out a lucky winner.
Okay, here
Awesome.
goes.
Can you read it out to us?
Karabo Maloka,
Awesome.
starting a Facebook page, facebook.com/distinction room.
Isn't that awesome, guys? Well done, well done, well
Congratulations.
done. You win all of this. Can you please share these chips with us? We're really looking forward to enjoying them with you. Thank you to Simba for giving us such wonderful prizes. And thank you to Macmillan for sponsoring the show, guys. This show is proudly brought to you by Macmillan. And big ups to you. Physical Science, Phil, are you still there with us?
Absolutely, I've been listening carefully.
Awesome. Please tell us what we'll be doing today.
Well, today we're going to be taking a look at projectile motion. Now, grades 10 and 11, I actually want you guys watching in on the show today because projectile motion deals with a lot of the stuff which you guys have already done before. And some of the grade 10s are just getting into this stuff. We're going to be dealing with kinematics. We're going to be studying what that word actually means. And I'm going to be showing you a couple of really cool virtual experiments at the website, which I'm going to put up on my presentation. My producer will show it to you later on, and we're going to be dealing with PHET, P-H-E-T. Now, even if you don't have time to put in the full address, if you just go into Google and you say P-H-E-T, it'll lead you to a really amazing site. So I'm just going to click on that link quickly and show you where it takes you. And what we're going to do is I'm going to show you how to get to the virtual simulations. Guys, it's amazing. It's really fun to play with. You are going to need a full computer to do this at. So if you're following us on the cell phone and the TV, just make sure that you write this down and that you can follow this through at a later stage. Okay, so I'm going to click on my link over there. So it's it's not www, it's http://PHET, so that's phet.colorado.edu/EN. EN stands for English, /simulations/index. Okay, so guys, there is the link. It's up on the board. If you're struggling to find it, just Google that part, PHET, P-H-E-T, and it should take you through all the way through to your simulations. Guys, you're looking for the All Sims or Play with Sims link. So what I'm going to do is I'm going to click on this link and I'm going to show you how amazing this page is. There's math stuff, there's life science stuff, there's even earth sciences inside here. But the main focus for today is obviously physical science. We're going to look for projectile motion, and that's the simulation that I'm going to look for. So I'm going to click on my link over there, and it's going to take me through to my web page. Okay, so what's happening over here is I've got all my simulations. Guys, you need to enable Java if it asks you any questions about, do I want to run Java now or do I want to install Java? Guys, Java is just something that your browser needs to understand some of these simulations. So you can see there's lots of simulations over here. I'm going to scroll all the way down to projectile motion over here, and I'm going to leave it open for later on. Now, I don't want you guys to get too distracted. There we go. So projectile motion, that one, I'm going to link it up, and projectile motion will come up. You'll see a picture of a cannonball flying through there, and I'm going to click on the link that says run now. So there it is. We're going to click on it, let it open up, and what you're going to see is a really nice playground. Guys, this is the most amazing virtual lab that you can play around with. I've got a cannon here on the left-hand side. I'm going to move it around a little bit. We can actually see that you can tilt your cannon in any direction. There's some numbers up on the right-hand side of the screen over here. We can even change what's going on, how fast the cannonball is coming out. Now, if you take a look at the menu on the right-hand side, I can even launch other things. And we'll all of a sudden get down to all sorts of weird things to shoot out of a cannon, like adult humans and pianos and cars and all sorts of cool things. I'm going to show you some cool things about projectiles when they're moving around. Now, here's some of you, especially if you teachers at home, worrying about, oh no, two-dimensional and all of this stuff. Don't worry about it. We're going to keep this one-dimensional. We're going to keep this straight up, straight down. Now, we might do a couple of things across to the side, but that's just as a demonstration. We're going to be dealing with objects which are just rising and falling. So that's the main focus of today. So let's get into today's lesson. Let's find out what we're going to be doing and what we're going to be learning. So there we go. Now, it might seem like a lot, but here's the gist of this show. There we go. So let's just highlight it as we go through. Okay, here we go. So it says that we've got to learn that all projectiles fall freely under gravity. Now, a lot of people get a little bit confused when they hear this fall freely. There we go. So fall freely under gravity and accelerate at g. That's a bit of a complicated thing. Whether they are moving up or down. Now, a lot of you at home are going, well, how can something be falling if it's going up? Okay, and that's a concept called free fall. We're going to deal with that a little bit later on in the show. Okay, so now I just want to start planting these ideas inside your head and say, okay, well, every object, whether it's going up or down, is accelerating because of gravity. I want you to think about that very, very carefully. Because gravity, if I throw something up or it's falling down, the only force acting on that object is gravity, but only if we ignore air friction. Now, for most objects, we can because the speeds are nice and slow. So if you're going to play with any of your normal projectiles, that's not an issue. Okay, now here's the part where you're going to get your marks. So I've got to use simple equations of motion to describe the motion. So we're going to be talking about displacement. So there we go. We're going to be using our equations of motion to describe the motion. So that's going to be dealing with some displacement. So either x or y. And then we're going to be dealing with velocity, and then we're going to be dealing with acceleration as we go through. And then what we're going to do is we're going to deal with some graphs. Guys, I know that you're saying, okay, graphs, I hope it doesn't come up in the finals. But guys, it's inescapable. It's been in every single final, guys. It's going to be in your paper. It was in last year's paper. It was in the year before that. Graphs of motion of vertically moving objects is inescapable. But the really nice thing is they've always got some tricks that we can start to look for to try and make this section a little bit easier. And then very lastly, I'm going to show you how to run through the steps on how to solve these, on how to take a look at equations of motion and graphs of motion. So here's the key to this. I need a structured approach. Guys, I see a lot of you saying, okay, well, equations of motion, cool, just write them all down. That's not how we want to do this. I want to give you some steps. I want to give you an approach. I want to make you feel good before you walk into that exam. So how do we do all of this? Well, first of all, let's tackle this little letter G. Okay. So this little letter G over there means something really, really important. Okay, now G, lucky for us, is a constant, and we're going to be dealing with this number. It's 9,8 meters per second squared. Now, you might have seen this already in grade 9. When I wanted to calculate the weight of an object, that is the gravitational force of an object, I needed this number. I took the object's mass and I multiplied by 9.8. If you don't remember that, don't worry, don't panic. It's not important today. I just want to show you that this number is everywhere as long as you're on planet Earth. And for most of us, that's going to be for quite some time, unless they get these space vehicles nice and cheap. Okay, so 9,8 meters per second squared. I want you to start thinking about what this actually means. 9,8 meters per second. Per second. Now, which objects are governed by these? Well, first of all, let's take a look at what a projectile actually is. So I say projectile motion, you say, what's a projectile? Well, a projectile is anything which moves without touching another object. So I've taken a couple of images off the web, And the first two are not everyone's favorite projectiles. Now, these are projectiles which are used to harm or hurt other people, but you can see that there's a tank firing a projectile on the left-hand side. The right-hand side is a really big picture of a bullet flying through the air. These are both projectiles. They're objects which move away, and they move separate from other objects. Now, they fly through the air. Now, what we're going to do is we're going to start taking it a little bit away from all these weapons, and what we're going to do is we're going to start taking a look at slightly more friendly projectiles. Okay, and the one on the left, I'm pretty sure most people recognize as a soccer ball, is one of my favorite projectiles. You can kick this to become a projectile scientist. Now, what we're going to do is we're going to describe this. We're going to see how these amazing soccer players playing in the CAF Cup. I hope you watched an amazing game. Nigeria, winners?
Yes, Nigeria
Okay.
winners. Well done.
Okay, so now, how do these soccer players do all these calculations? How do they figure out where to put the projectile? Now, after this lesson today, you guys can calculate for yourself how high the ball should be, in which direction it should be going, okay? So guys, projectiles are everywhere. Even if you decide you're going to throw a ball to your friend at break, or whenever you're kicking around a soccer ball, or even shooting an arrow, something like this. These are all projectiles. Now, here's the thing about projectiles. They've all got something in common. As long as I'm shooting a gun, or I'm kicking a ball, or I'm shooting an arrow, I'm on Earth, and I'm subject to Earth's gravity. Gravity is always going to be pulling me down, and every object is going to have weight pulling me down. Okay, so guys, just make sure that you've got this idea that gravity is always a force which is acting downwards on objects. So whether it's a bullet, whether it's a soccer ball, whether it's an arrow, gravity is going to be pulling down on all of these objects. Now, here's the thing. This is the really weird thing, and this is something which people really don't believe me in. Gravity is constant for every single object. Okay, and that's quite a weird thing. Okay, this value applies to every single object. Now you say to me, okay, no. There's something wrong here, Phil. What's happening? 9.8 meters per second for every object. If I decide to drop a car and I decide to drop, let's say, a pencil, how is it possible that they're going to accelerate at exactly the same amount, or the same rate at least? 9.8 meters per second. That's kind of weird. How is it possible that they will always speed up at the same rate? Now, grade 12s, you guys, if you've been listening very carefully to some of the Newton stuff that Tracy was doing so amazingly, and if you remember from last year, okay, gravity does two things to a heavier object. Gravity will pull harder on the heavier object. So let's just picture this. I've got a pencil, I've got a car. Just imagine I can pick up a car with my one hand. Maybe one day I'll be strong enough. But I've got a pencil in one hand, I've got a car in the other hand. Now, which one does gravity pull on more? And all of you are going, why is he even asking this? The car, definitely. The car is being pulled down with gravity more. And you're absolutely correct. But think about this. Newton's second law says that acceleration is inversely proportional to mass. Now, I don't want you guys furiously writing down. I want pictures inside your brain. You're saying, okay, well, the car has more weight, so gravity is pulling harder on the car. But the car is more difficult to accelerate as well because of its larger mass. So gravity does pull it harder, but it's much more difficult to accelerate. So what you're finding is they will all cancel out. Here is the magical number. Now, if you guys still don't believe me, and you guys are picking up plates and you're picking up pencils and stuff at home and going, look, watch and you're dropping everything on the floor, okay, you're going to find that they're always hitting on the ground at exactly the same time. Now, I've actually done an experiment before this because it's quite difficult to do this in studio and get it accurate. So I've put up a virtual experiment and we're going to play around with it in a moment. But let's get our key concepts in there. So what's happening here? Gravity accelerates all projectiles downwards. Now, every object, whether going up or going down, is going to be accelerated at exactly the same number. And this is called G. G for gravity, it's a gravitational acceleration. What else do I need to know? Okay, there we go. Rising or falling. Guys, that's hugely important. If an object is going up or it's going down, nothing is different. Gravity always applies. And this is the reason that objects, while they're going up, will slow down. While they're going down, they will still speed up. Now, I want you to say, okay, well, those are two completely different things, Phil. That's not entirely true. If you're paying attention to your direction, acceleration is always pulling towards the ground. So while it rises, gravity is pulling it backwards. While it's falling, gravity is pulling it downwards as well. So gravity is always pulling downwards with the same acceleration. Guys, I can't emphasize this enough, because remember that gravity and acceleration itself are vectors. It's got a magnitude. Here we go. So let's write this down. So it's got a magnitude over there, and it's got a direction. Guys, it's always down. I don't know what planet you're on where gravity acts up, but gravity itself, 9.8, is always pulling me down. Okay, I feel it when I get out of bed. I feel it when I try jump up. I feel it when I run, jump, do anything. I can feel gravity is always pulling me down. So there it is, magnitude and direction. Now, some of you are still going, I don't believe this. Drop a card, drop a pencil, hits the ground at exactly the same time. Okay, so what we decided to do at the school where I work is we did a virtual experiment. Now this, I've blocked out their faces because some of them would be quite angry if I put it up there. And we did a virtual experiment. So what I'm going to do is I'm going to ask the producer to put this up on the screen. And we're going to try and see that all objects move at exactly the same speed. So what I'm going to ask you to do is to follow two objects. So the first object I've got over here is a rugby ball. So there we go, rugby ball number 1. Now what I'm going to do is I'm going to ask you to follow the second object over here, and that is a teddy bear. So what we're going to do is we're going to follow a teddy bear and a rugby ball as they start to move all their way down. So I'm going to mark the rugby ball over here, so I can see that the rugby ball is moving down very, very nicely. So there's object number 1. Now what's happening here? And you might say, how on earth did this picture happen? This is the same picture taken 1/8 of a second apart. Now, I don't want you to get caught up in the details. I want you to watch what happens. So as the objects fall, they start to speed up. Now, I want you to notice about the spacing between the rugby balls and the teddy bear. Now, a teddy bear weighs almost nothing. Rugby ball is pumped hard. It's very, very quick to fall. And what you can actually start to notice, now I'm going to mark the teddy bear with some green arrows. And we're going to move this around a little bit, so if it's getting cluttered, don't worry about it. What you'll notice is that the teddy bear itself is falling exactly at the same speed as a rugby ball. It doesn't matter how far down we go, you can see that the rugby ball over there is matched by a teddy bear. Every rugby ball has got a matching teddy bear. The teddy bear manages to keep all the way up with the rugby ball through all of these frames. So what we're finding is that a teddy bear, which weighs almost nothing, is capable of accelerating at exactly the same speed as a rugby ball. Now what we're going to do is we're going to make sure that we can get rid of all these arrows first. So let's just move them off the screen for the moment. And we're going to do another test. A lot of you are kind of going, well, I can't really see what's going on in the photo. So what we're going to do is now we're going to play around with our smiley faces teddy bears and rugby balls. And what we're going to do is we're actually going to measure the differences between these two frames. That tells me how far something's actually fallen. So in order to do that, we're going to grab an arrow marker. I'm actually going to change the color of this to make this a little bit more solid. There we go, right? So what I'm going to do is I'm now going to measure the difference between these. Okay, so what I'm going to do is I'm going to pick one particular frame. Let's pick the one down at the bottom because I can see that nicely. So from one teddy bear to the next, what I'm going to find is that when I start moving it across to the rugby ball, it matches exactly. Now you might say, okay, well, what about all the other balls? They seem to be a little bit ahead or behind. What I'm going to do is I'm going to show you that the same thing has happened to all the other balls inside this picture. Doesn't matter if I've moved across to the volleyballs, or if I've moved across here to the soccer ball, or even to the basketball. The spacing is exactly the same. What I'm finding is that all these objects, doesn't matter what the mass is, have accelerated to exactly the same speed after the same amount of time. And guys, if you're paying attention, that means that all of them were following that g value of 9.8 meters per second. And when we did this calculation at school, guys, we actually found very close to this actual value. Now that's quite difficult to believe, but all of these smiling faces are telling me that 9.8 is absolutely true. Guys, while I let that sink in and while you get some stuff to drop, I think we should give them a little bit of a break.
I think they deserve that break. Well, Phil, what a fantastic photo. And you guys, I know are enjoying it because you're on the page and you're chatting. Tebogo, how did that feel?
It was a wonderful experience. I really enjoyed it.
Thank you very much. And Tebogo will be on the page. Do you want to tell them where they will find you?
Yes, on www.facebook.com/learnextra.
Awesome. So guys, you can chat to her, ask her how it is to be a top 10 presenter on Mindset Learn Extra, and we will be seeing you guys right after this insy-witsy break. Welcome back, Mindsetters. If you have just joined us, which I hope you have not, we are doing physical science for grade 12s, and we have also had a random draw for our random acts of kindness. Guys, Karabo has just won everything that you see around me right now, the Simba chips, Cheetos, the Universal CDs, the Mindset lanyard and pens, this from Simba. Guys, this all goes to Karabo. Well done. What he has done is that he has jumped onto Facebook and he set up a page for everyone to join him there, just so that he can give back to others by helping them with accounting and maths. He says that he's really passionate about this, and it hasn't just started now. He used to struggle with accounting and maths and science, and he says he used to struggle with it, but now because he's learned so much more extra and he's learned so much more, he is now giving back to everyone. Guys, this just shows us that if you want to give back to others, it doesn't take much, guys. You don't have to pay for anything. You don't have to buy anyone something. It's just about doing something that makes someone else smile. Guys, no one has to pay for a smile. Just about helping someone cross the road with their bags. If you see someone struggling to get into a taxi or a bus, you just say, hey, can I actually lend you my hand, and so that I can help you up? Or helping your mom and dad when they come back from work, giving them a foot massage, offering them to cook, helping your little brother with his homework. Anything that you need to do, guys, just to put a smile on someone's face. People have even said they just walk up to someone and give them a high five, and that's all, and that makes someone smile. Or just a tight squeeze, a hug and a kiss. Anything that it takes, guys, it just shows you that it actually takes nothing. It actually takes nothing. Just a smile from you can make someone else smile. So thank you for that, Karabo, and well done. It is the month of love, so keep spreading love, guys. Over to you, Phil.
Thanks so much, Kath. Okay, guys, I just want to go through some of the details on this photo again. I just want to deal with this issue of 9.8 meters per second squared. I hope you guys haven't been dropping some dinner plates, like Kat says, helping out your parents. Okay.
I don't think that would help them.
No, not at all.
So angry.
Okay, so, I mean, the whole idea is that every single object will accelerate at the same rate, no matter what it is. Now, some of you are going, No, Phil, what about a piece of paper? What about a feather? If I drop a heavy thing and I drop those, what's the difference? Okay, well, if I drop a pen and if I drop a feather, all of you are going, oh, well, pen dropped down, feather was lighter. That's the reason that it fell slowly. Now, that's not entirely true. Now, a feather is lighter than a pen. That is absolutely correct. But a feather has got something that a pen does not. What a feather has got is a large air resistance. It's got a very, very large surface area. Now remember that 9.8 is only for objects which are in free fall. That means acted on only by gravity. So generally that only happens when things are moving quite slowly or they don't have a lot of air resistance. So before the break, I showed you that if I've got a teddy bear or I've got a rugby ball or a netball or if I've got a soccer ball, doesn't actually matter. Okay, and I'm pretty sure that you'll recognize we've got a World Cup soccer ball over there, and we've got a volleyball over there, and we've got a rugby ball over here, and a teddy bear. Doesn't matter what it is, it's falling at exactly the same rate, and you can see that the same photo taken for those objects is roughly the same size. So you can see it depends. Some of them have turned around a little bit, but exactly the same spacing. Doesn't matter which object, every single object speeds up, accelerates at exactly the same rate. So what we're going to do is we're going to take a little bit of a look at what projectile motion actually is. Now, this is all about the up and down. I want you guys to jump on that FET page. We're going to do something fun with a Java simulation. So for those of you that are not IT geeks, okay, doesn't actually matter. I just want you to go Google FET, find it, and play along with us. So here we go.
And the link is up on the page.
Absolutely, guys.
Check it out.
Check it out on our Facebook page, the link to this fantastic, and this, I can play around with this for hours, and I'll show you why in a moment. Okay, now projectile motion usually deals with something like this. What I'm going to show you now is what happens when I fire a cannon almost directly up. There we go. So if you decide you're going to shoot a cannon one day directly up. So what we're going to do is we're going to start off with something which is normally conventional, like a tank shell. Okay, So on the right-hand side, I can actually see that there is an initial speed over here. There is a mass of the object. Doesn't actually matter, but I want you to keep an eye on the mass of that object. So what we're going to do is I'm just going to show you what I want you to keep an eye on. Okay, so there we go. So what I'm going to do is I'm going to draw around here. Here we go. So there we go. The mass of the object. That mass I want you to keep an eye on. Guys, when you change objects, you will change the mass of your object. And what happens is that it doesn't matter which object, what you're going to find is that the same thing is going to happen. Now, the other numbers which I want you to keep an eye on is the height and the time. If you're feeling very adventurous, you can follow the range, but that's not important at all. So what I want you to keep an eye on is the height that it reaches and the time. So when I fire this bullet, let's do exactly that. So you'll see that I've got an option here. It says fire. And what I do is it actually follows the trajectory. Now that's a word that tells me the path of a projectile. So if I say I fire it and I can see my tank shell, it goes up and it falls down exactly. So what you can see is that I've got a height and I've got a time and it's followed exactly the same thing. The reason that it's gone to a negative height over there is because my bullet has actually buried itself inside the ground. So 1.2 meters underneath. So let's just do that again. I want you to watch the maximum height. You can see that it's reached up to a maximum height of around about 16.4. Now, you're thinking, what happens if I put other things inside my cannon? So let's just do this again. So I see you guys looking at that drop-down menu, and some of you are going, there's way more fun things. So I'm just going to reload my page. And what I'm going to do is I'm going to put some other things inside my cannon. We're going to change the mass. We're going to change into a golf ball. We're going to change into a tennis ball, and maybe even stick a car inside a cannon.
Wow.
Okay, so let's do exactly that. So let's start out with this. Let's go big. Let's put in a pumpkin. I want you to notice that the pumpkin's mass, 5 kilograms, is up there on the screen. Let's follow exactly how high it goes. And I want you to play around with this. So I want you to see that if I fire up a pumpkin, it does exactly the same thing as a tank shell. Now you're thinking, okay, well, a tank shell is big and it's heavy and it's made of metal, and if I fire a pumpkin at exactly the same speed, it's going to go to the same height. Why, guys? What is the common factor between a tank shell and a pumpkin? They're both working against gravity. Both of these objects are fighting against gravity. Now, let's change this even more. Let's change this to another object. So what I'm going to do is I'm just going to freshen up my page. I'm just going to let it load again. I want you to picture what happens when I get a much, much heavier object inside there. And this is one of my favorite ones. We're going to keep on shooting it up. Now, my kids laugh at me a little bit, and it's a little bit crazy. So I just want to make sure that my cannon is facing directly up. There we go. And right down at the bottom of my list, I can see an adult human.
Sure.
We're going to see what happens when we shoot people out. Okay, so we're going to shoot an adult human out of the cannon. We're going to have a human cannonball going up, fighting against gravity, and then losing the fight against gravity and smashing on the ground.
Wouldn't
Okay.
that be awesome?
Well, I'm not sure that the person inside the cannon would agree with you, Kat.
I don't think so either.
Okay, so well, let's see what happens. Okay, so we're going to have our adult human. There we go. We can see them. They don't seem too happy about this, and then smashed on the ground.
Oh,
So we can
shame.
see that they look quite unhappy about that.
Yeah, they're
But we
not
can
too-
see exactly the same result. They both, the pumpkin, the tank shell, the human being, they all went to exactly the same height. Now, what I'm actually going to do is I'm going to go slightly away from the syllabus, but it's still in keeping with something fighting gravity. Now, guys, inside your textbook, you will find this section, but guys, it's not examinable. Okay, what I'm going to do is I'm going to now move this, and we're going to start talking about a little bit of 2D. It's very seldom that you actually just kick something up and down. When somebody comes up to the goals and they want to kick a soccer ball, they don't kick it up, they kick it towards the goal. So they kick it up and forwards. And that's what we can do with our cannon. So what we're going to do now is we're going to change the direction of my cannon, and we're going to fire our human being in a different direction. So let's do exactly that. So I'm going to fire the human cannonball. There we go. We see them flying off the screen over there. There we go. Right, we've missed our mark. Now what I want you to see is that no matter which object, now a Buick is in a big American car, so we're going to fire a big car, and we're going to do exactly the same thing. Same speed, same angle, but much, much bigger object, much bigger mass. But remember that all objects are governed by exactly the same acceleration. So if we push fire, what should happen? Well, you can see that it follows exactly the same path. And there we go. We've got a big wreck on top of the person, not a very happy one. But you can see that no matter the object, we can see that it moves exactly the same way against gravity, whether it's going up or down. So guys, I want that firmly planted inside your brains. Now let's see how we change this into metric marks. So let's get back to what we're doing over here. How do I get this onto the page in terms of equations of motion? And let's do exactly that. Okay, so what I'm going to do is I'm going to take you through a very simple example. A ball which is dropped for a period of 2 seconds, which is exactly the example which I gave after that experiment in the picture. So I've got a period of 2 seconds. The first thing I want you to do is read the question, obviously. A lot of you are just browsing over going, okay, well, I'll sort this out. Let me get an equation and put some numbers in. Guys, I can tell you now that is a recipe for failure. Guys, don't just get an exam and, oh, okay, I've got all my equations, no problem. Let's find some numbers. Let's jam them in and get a number out, write it down on my page and get my answer. Guys, please. There are steps. The first 2 steps don't get you any marks. And you say, well, why should I do them? Well, they're going to set you up for success in your 3rd step. Here we go. Diagram and direction. This is probably the most important. This is where you win or lose your battle against equations of motion. Just having a good diagram and a firm grasp of your positive direction. So let's take a look at the diagram which I've drawn. If I want to calculate the final velocity of an object, let's start this out. There's a couple of words on the screen which I want you to pay attention to. There we go. At the beginning, initially, I've got my projectile over there. It's up at the top. It starts at 0 meters per second. They might not tell you that it starts at 0 meters per second. But if they do, they usually add the word from rest. So just as you and I like to rest at 0 meters per second stationary on the couch, I start from rest, so 0 meters per second. Then it's going to fall for 2 seconds. Downwards, why? Well, gravity is going to win this fight. And then finally, it's down at the bottom there somewhere. There's something else which I've done on this picture. I've put an arrow with a big cross over here, and that is a plus. That shows me that upwards is my positive direction. Now you might say, well, the thing is moving downwards. This doesn't actually matter which direction you've chosen as plus or minus, but once you've chosen, stick to it. Matrix, please pay attention to your positive direction. I'm going to show you why that's important in a moment. So now I've got a good diagram. I've got an object moving down for 2 seconds. Let's see how I set this up. Now here it is. Tabulate. Guys, you're saying, okay, well, what's a table got to do with a ball falling out of the sky for 2 seconds? I've got to tabulate my information. I'm going to show you exactly how to do that. So what I tell my matrix, my grade 11s, is I ask them to make me this list. All right. I start out with my 2 velocities, then my time, then my acceleration, and my displacement. You might notice that I've used Y because it's a vertical example. Okay, so a quick way to remember this is VV-tax for horizontal or VV-tay. So VV-T-A-Y. So there we go. So let's just highlight them. So VV-T-A-Y. This gives you a really nice shopping list for finding your values. Put a nice equal sign for each one of them, and let's start collecting my information. Well, first of all, I know that I've got an initial velocity of 0 meters per second. And there it is. I got told that it was falling or being dropped from the top. My V final, I don't know. That's a question mark. That's what I'm after. What about my time? Well, I was told that my time was 2 seconds. And here's the other thing which they will not tell you, is that acceleration is in there. And it's negative 9,8. I want you to write it in your table with the correct sign. Now, it's not always negative 9,8. It depends on what you guys chose as a positive direction. I chose that up was positive. Gravity acts down, so gravity is negative. So there we go. Let's take a look at the last one. What about displacement? Well, we weren't given it. We weren't asked it. So what I want you to do is to say, okay, well, for the moment, I don't really care about displacement. Now, here's the trick, guys, and you'll see it in the notes if you take a look online. I've actually told you how to select the correct equation. Now, a lot of you are saying, okay, well, that's easy. I've just got to find an equation with VI in it, with VF in it, with T in it, with A in it, and you guys are going to be sitting there for 5 minutes trying to figure out which is the right equation. It might seem simple, but the easiest way to find the correct equation is to find the one with no delta y. That means that you're only looking for one thing. I want an equation without delta y, guys. That's by far the easiest way to sort this out. Okay, so you've drawn me a diagram, you've given me a direction. Now, tabulate is my second step. So then, here comes the magic. This is where I can go to my equation. So now, what I'm going to do is I'm actually going to select that equation, and there it is. That's the only equation without delta y. Okay, so now I substitute without drawing on it, mind you. So let's just make that nice and neat for those of you taking notes. So now I'm going to substitute. Notice how I've kept the negative 9,8 over there. The time is always going to be positive, so just take note over here. So I'm just going to highlight it as I go. So my V initial, I've got it. There it is, 0. It's been substituted in. Negative 9,8. Guys, I can tell you now, if you're having problems with equations of motion, it's your signs. It's your plus and minus, that's it. It's very, very seldom at a grade 12 level is it a maths problem. If you've got a maths problem, just approach your maths teacher and say, I've got a problem with linear and quadratic equations. Guys, you should have this sorted out from 11, but if you're still having problems, just approach them and say, well, here's my problem. I can't figure out what's going on here. But for most of you guys, if there's a problem, that negative over there is causing all of your hassles, and I can guarantee this 9 times out of 10, that is the problem. Then I move onwards to my time. There we go. Very nice thing about this. All I need to do is to put this all in my calculator or calculate it very, very nicely. There we go. We've got a negative velocity. But now you're saying, well, how can I have a negative velocity? What does it mean? Well, your teachers are saying, okay, well, it's negative. What does it mean? They're going to penalize you if you don't put that negative, and then they're going to penalize you again if you don't rewrite your answer in a positive way. Always rewrite negative answers with a direction attached. This negative means downwards in my case. Now you say, is negative always down? No, matrix. Stop looking for tricks. I want you to understand that I chose up as positive. Negative means down. Now, what we're going to do is...
So, actually, before you carry on, Kopano actually has a question.
Yes.
If an object is thrown up or it is falling down, is the value of G always positive? I know you've just answered that.
Ah, very good question. Okay, well, the value of G is always 9,8.
Yes.
But it can be positive or negative depending on which direction they've chosen as positive.
Oh, okay.
Okay, so I've chosen up as positive, so G over here will be negative. But if, guys, if you've chosen down as being positive, then this will be positive 9,8. I will get a positive answer here. But the end result, this end result over here, will be exactly the same. That's the magic of vectors.
Okay.
If I follow my steps correctly, it's always going to come to the same answer, guys. Please be careful about that plus and minus. Nice question.
Thank you, Phil. Thank you.
Okay, well, guys, what I'm going to do is I'm actually going to give you a little bit of time to stew over this. We're going to go to a short ad break. We're going to get back to another quick question.
Awesome.
And then
Thank
jump
you,
into
Phil.
that exam question.
Guys, remember, jump onto the page, ask questions. Tebogo is also on at the back answering your questions. Please engage her, chat to her, and see what's up on the page. Guys, it's really awesome. You matrix are really, really getting into this. So keep chatting to each other. We'll see you right after the break. Welcome back, Mindsetters. Wow, we've been having so much fun in the studio, guys. I don't think you understand how exciting, but also how important this section is. I hope that you guys are really, really glued really tightly to your screens and your couches. Also, I wanted to show you something really awesome, and that's this textbook by Macmillan. It's Physical Science for All, guys. I know that some of you do use it, but guys, get your hands on one of these. It's really awesome, and thank you, Macmillan, for this. They are really great mindsetters. Get out there and photocopy or find yourself this copy or ask your teachers for this. Guys, go crazy. There's so many awesome physical science stuff in this thing that you guys can really, really get to use. It's really, really great. I don't think you understand, but I know you do, but I don't think you understand how great Macmillan is for giving us this thing to use as well. Over to you, Phil.
Thanks so much, Kat. Okay, well, what I'm going to do is, some of you have said, what happens if I have an object which goes upwards? Okay, now this is the one that I really want you to concentrate on. Here we go. Here's my ball, which is projected upwards. All right, there we go. Thrown upwards, and there is the velocity at which I threw it up. Now, some of you are saying, okay, well, what's the difference between meters per second to the -1 versus to the -2? Now, when I see a -1 over there, that tells me that this is a velocity and not an acceleration. Guys, make sure that you don't get confused. Okay, so what I'm doing is I'm going to say, all right, there we go. I've got an initial velocity of 19.6 meters per second at the bottom. I've drawn in my positive direction as up, but here's the thing, a maximum height. That means something. This means that my final velocity is equal to 0 meters per second. Now I want you to say, okay, well, how was I supposed to know that? Guys, think about what happens when you throw an object up. It stops up at the top. That's the important thing. So when you throw an object up, it's got a velocity when it leaves your hand, and it stops up at the top. Now, Matrix, another misunderstanding that a lot of people have is that I'm talking about an initial velocity inside my hand. It's only once it's left my hand and is flying through the air. I can't consider this object a projectile while it's still inside my hand. So I'm not talking about an initial there or an initial there. What I'm talking about is when it leaves my hand and flies upwards. So what we're going to do now is I'm going to take you through going from my initial velocity up to my final velocity. How far did it go? Well, guys, simple diagram, positive direction up. Let's look at my table and let's see what equation we should use. Okay, so as I told you, diagram and direction is the most important thing. Let's fill in my table. Okay, so once again, VVTAY is my shopping list for information. There we go. So V initial, V final, my time, acceleration, and my displacement, except there's one difference. Take a look. I don't have the time. I don't want the time, so there's the way that you're going to find your correct equation. So there we go. Cross that one off your list. If I look for an equation without time on there, I'm going to find my equation that I'm going to use. So let's just make sure that you've paid attention. My initial velocity is up, and that's positive 19.6. My V final, because this was a maximum height, is 0 meters per second. My acceleration, guys, is negative. Guys, please, gravity always acts down, and I've chosen up as positive. So gravity itself must be a negative value. Okay, now guys, I'm hearing a lot of questions. Why the -2 or why the -1? And I think Kat's answered the question on the page.
Yeah, I have.
All right, so acceleration. Acceleration has got the value of -2 over there. You've got to have -2. It actually means meters per second, and that's a change in velocity per second. So meters per second, per second. You're saying per second twice, and that's why that 2 is over there. Okay. So let's figure out which equation to use. There it is, the only equation without time. I can see that there's no time. It's much easier to check for one thing which is missing rather than all 4 of these. So there we go. So as we go through, my V final I've got, very nice. My V initial I've got, fantastic. My, well, 2 you always have, it's just a number. And then acceleration I've got. The only thing which I don't have over there is my delta x. So I've got everything except delta x. Now, some of you might use delta y. It depends on which equation I've used, but you can use delta y or delta x. Now let's substitute. There it is. All we've got to find is my displacement. There we go. I find a positive value, 19.6 meters upwards. Now, since it's positive, I don't need to rewrite it. Now, before we move on, guys, I want to show you something really cool. What we can do is we're going to take our 2 examples, and now we're going to put them onto graphs. And some of you are saying, no, Phil, no graphs, please. Guys, graphs really are not that hard. I'm going to show you just how easy that can be. So I'm going to take example 1, we're going to graph it. Example 2, and graph it. I'm going to show you all 3 graphs. So I want you guys, if you guys have downloaded the notes, easy. You've already done the notes. And take a look at what happens when we start to graph these things. Now you're saying, okay, well, Phil, why are all the graphs going downwards? Well, it's to do with my positive direction. So what we're going to do is we're going to take a look at my y, we're going to take a look at my v and the a. Now what does this all mean? Okay, well guys, y, remember, is my vertical displacement over here. So let's highlight it. There we go, my vertical displacement, my velocity, my acceleration. I'm graphing all 3. Now you might say, okay, well, which one's the easiest one to start off with? Now guys, here's just a little bit of a tip. Acceleration time is by far the simplest one. Notice the value over there, negative 9.8. I think I've blocked it out a little bit so you can't read it very nicely. But there it is, negative 9.8. It stays the same whether an object is moving up, falling down, or even stopped up at the top. Guys, 9.8 downwards always. Always, 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 always. And I can't emphasize that even enough, because everyone seems to forget, okay, well, something different happens when something falls or goes up. No, the acceleration is always the same, whether it's going up, stopped at the top, or going down. The whole time, I've got negative 9.8. Now, here's where the trouble comes. Velocity time. What happened at the beginning? Well, if you're smart, and I think you are because you're doing physical science in grade 12, here we go. That's where I started, at 0 meters per second. Now, the question is, what happened to the velocity? Well, you said, okay, well, for 2 seconds, the object accelerated. You saw the teddy bear, you saw the rugby ball. It was falling. Its velocity was increasing. But why is the velocity going down, Phil? What's happening over here? What I'm finding is that my velocity is becoming increasingly negative. It's going faster and faster down, guys. So you can see that the final value over there is negative 19.6, which is the value that we calculated. I want you to notice that that's a straight line. That means that there is a constant change in the velocity. Now you say, okay, well, what are you talking about, Phil? How do I change velocity? Well, a change in velocity is because of acceleration. I'm pretty sure you can guess what the slope of this graph might be. The slope of a VT graph, remember, is my acceleration. And the acceleration for an object all the time is negative 9.8. Guys, this is really amazing. You can actually see on a VT graph that your velocity is changing by 9.8 meters per second every second that goes by. That is my gravitational acceleration. Now, slightly more tricky is my displacement time graph. Now, here's a trick to remember. When there's acceleration, I'm going to have an exponential graph here. Now, you guys are saying, okay, well, please, Phil, enough with the maths. Okay, well, let's keep it simple. If the speed changes, the slope changes. It's as simple as that. Now, guys, you can actually grab your ruler and do something quite cool when you take a look at a displacement time graph. I want you to use your ruler as a speedometer. I don't know if you can actually see it very well, but let's take a look and let's bring down my ruler and let's play around with our ruler. Okay, so there we go. You got your ruler, you've got your displacement time graph. Your ruler is your speedometer. If your ruler is flat, I'm stationary. This is how your ruler should be. The steeper your ruler changes, the faster the object is moving. Now, guys, this is only for your displacement time graphs. So I'm going to show you how to use your ruler correctly now. So I start my ruler over there right at the beginning. Then what happens is as I move, now watch what happens. My ruler's not in line anymore. So what I need to do is I need to move my ruler. Take a look. My ruler's become steeper. So as soon as your ruler starts to change its angle, that means that I'm going faster or slower. Anytime that changes, faster or slower. It's like a speedometer in a car. As it goes steeper or slower, that means that my velocity is increasing or decreasing. Remember that my slope on my displacement time graph is my velocity. But because it's a curved line, it's quite difficult. So, once again, let's move our ruler around. Let's move it along to the end point, but I need to make it a lot steeper to match up with the line. And what you can see is that it's gone even faster and faster and faster. Now, this is what's happened with my displacement time. Let's see if you guys can guess what these three graphs look like for the next one. So example 2, what about a ball which is thrown upwards at 19.6? Okay, well, acceleration time, there it is, predictable, nice, negative 9.8 the whole time. If you've been listening very carefully, something else has happened. I threw a ball upwards. For my velocity time, that means that I started off with positive 19.6. What happens? It reached the top, and that means that it stopped up at the top there. So after 2 seconds, it struck the top. How did I know 2 seconds? Well, guys, you could actually calculate how long it takes to stop a ball which is traveling at 19.6. Now, there must be a reason that Phil chose this number. It's exactly double 9,8. So for every second that goes by, I decrease my velocity by 9,8 meters per second. Now, the right-hand graphs, the VT and the AT graphs, these are pretty easy to understand. But here is the problem. My displacement time graph. That's the complicated one. So what do? I reach for my ruler and I try and find out what's the gradient. How steep is my ruler on this graph? So let's do this together, grade 12s. So if you've got the notes in front of you, good for you. If you've printed them out or you made copies for a friend, guys, please distribute them as much as you can because they are there. They are for free. Mahala, they're yours, guys. So what's happening over here? Let's take a look at my ruler. Is it steep or not? Is my car fast or slow? Okay, now this is not a car. This is an object which is falling through space. Take a look. It's steep, guys. That means fast, really, really fast. How fast? 19,6 fast. Then, let's take a look right at the end. Let's change our ruler so it actually matches up there. You can see that my ruler has to become flat to agree with my line there. That means that it's stopped, guys, and that's exactly what happens when a ball reaches its maximum height. Quite a difficult question, but one of the reasons that I wanted to tackle this is because it came straight from a past paper. An object was thrown upwards, and guys, you had to graph this all out. And please, 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 and this is the thing, which I cannot implore you, doesn't matter if it's going up or coming down, negative 9,8, as long as up is positive. Guys, please make sure, absolutely sure that you understand this. Guys, if you want a little bit of a challenge, I'm going to put one up. I'm not sure that we're going to get time to go through it, but here it is anyway. So what we're going to do is, hold on, there we go. All right, there we go. This is a past paper question. Guys, inside my notes, I've left links to all of these past paper questions as well. You can go and download the past papers, practice your way through them. I just want to show you how it looks in an exam. I want to show you how to approach this quickly in the last minute or so that I've got. Okay, here it is. A supervisor, 1.8 meters tall, visits a construction site. A brick resting on the edge of a roof 50 meters above. There we go, that might be important. Right, and the supervisor's height, it says. The brick resting suddenly falls. There we go. As soon as we know that it suddenly falls, that means that it, A, starts from rest and accelerates at 9.8. At the instant when the brick has fallen 30 meters, the supervisor sees the brick coming down directly towards him from above. Complicated passage, guys. Highlight your words, get your information. It says ignore the effects of friction, good, and take the downwards motion as positive. So I want you guys to draw this out. Now what they want you to do is to calculate the speed of the brick after it has fallen 30 meters. So guys, if you're looking for a little bit of a challenge, the solution is up on the web. Follow through with our notes. Try this out. See if the supervisor is going to get hit on the head or not. I'll check back with you next week.
Thank you very much, Phil. So guys, you heard what Phil said. We have such an awesome site packed with notes, okay? So you guys need to go there, check it out, download the notes, print them out, stick them on your TV walls, not the actual TV, because you need to still see us. The walls around the TV, in your bathroom, in your bedroom, give them to friends. As Phil said, guys, mahala, free. Print them out and send them to all your friends, guys. They will really appreciate you. Remember, those random acts of kindness, this could be your random act of kindness. Send your friend the link. Remember, the link is www.learnextra.co.za/live. Guys, check it out. It is amazing. Well done to Karabo again for winning that prize, guys. All the prizes, as you can see around me. Well done to Karabo. Remember, guys, we're still seeing your random acts, guys, so keep posting them through, because every week for another 2 weeks, there will still be some prizes up for grabs. Thank you to Macmillan, guys, for sponsoring the show, and thank you to you guys for joining us. Goodbye.